This question is about finding the distribution of a random variable which is a function of another random variable, and that another random variable, for that another random variable we know the distribution. Okay, so in this case we have a random variable x which is uniform in the range -3 to 2, and we have a function of this random variable which is the mod function of x. Okay, so through this function we get another random variable y. Okay, and y is a function of x. So our goal is to find the distribution of mod of x, or equivalently we have to find the PDF of mod of x. So we have to find the PDF of y. So let's first calculate what's the PDF of x. So PDF of x will be 1 by difference in the ranges, because that's how we calculate the PDF of any uniform random variable. So it will be 1 by 5. We know the range of x, we know the PDF of x. So we know everything about the distribution of x, and using this we have to find the PDF of y. So we already know that if we have a random variable which is a function of another random variable, and we have to find the PDF of that random variable, then we need to find the CDF of it first. So if we, in this case, if we need to calculate the PDF of y, we need to first determine the CDF of y, because finding the CDF will be a little easier. Okay, so we will first find CDF of y. Okay, so before getting to the CDF, let's first find out what's the range of y. Okay, since y is a mod function, so y will have the minimum value 0, and it can only take values in the positive direction. Okay, so even if it is a function of x and x can take negative values, y will never take any negative value. So the maximum value of y will be taken when x will take -3 value. Okay, so -3, it will become +3, that will be 3. So y will be in the range 0 to 3. So we have to now get to the CDF of y. So we can write CDF of y as capital Fy of y. We are calculating CDF at some small y, okay, and y falls in the range 0 to 3 in the range of y. So we can write it as probability that this random variable y will take value less than or equal to some value small y in its range, in the range of y. So how we can write it? We can write it like this, then again can simplify it. X will fall in the range -y2. So as you can observe here, initially we had the problem of finding the CDF of y, and we converted it into in some form that requires calculating some probability of x, and we already know everything about the distribution of x, so we can easily calculate this probability by just integrating the PDF. Okay, so we can calculate this probability by integrating the PDF of x, okay, which is 1 by 5 from -y to +y. Now the next step that comes to mind is, just put this value of fx here, the PDF of x, and integrate it and find out the CDF of y. So let's try to understand why that direct approach of integrating the CDF, okay, just putting here 1 by 5 and integrating it, won't work here. Okay, we will have to think a little more carefully. So let's consider two cases. The first case is when we have to find out the CDF of y at some value less than 2. Okay, so fy at 1.5. And the second case we will consider when y, we have to find out the CDF of y at some value greater than 2. So how will you do that? It's very straightforward, right? We can just write, just like we wrote in the previous case with generalized example of y, we can write the same thing here, that this y will be less than equal to 1.5. Similarly here, y is less than equal to 2.5. So we can do the same simplification here that we did for the general case of -y and +y. We can write it as the probability that x will take values between -1.5 and 1.5. Here also we can do things in the same way. When when x falls in the range -2.5 and +2.5. Now notice one thing here. Does x have a range between minus 1.5 and 1.5? Is it a valid range for x? Yes, it is, because x has a range from minus 3 to 2. So x will definitely fall in this range, that is minus 1.5 and 1.5. So we can calculate this probability just by integrating the CDF of x, okay, from minus 1.5 to 1.5, because this falls in the valid range of x, okay, and we are done. We will be able to calculate the CDF of y at 1.5. But think about this case here. Does x fall in this range? Okay, yes, it falls from, okay, it can take values minus 2.5, but it cannot take values 2.5. Okay, it cannot take values greater than 2. So we can further break it down into two parts, into the parts where x takes values and where x does not take values, right? So we can write it as the probability that x will fall in the range minus 2.5 to 2 plus the probability that it will fall in the range, x will fall in the range 2.5. Okay, and you can immediately observe here that this will go down to 0. Again, we will be left with only minus 2.5 and 2, right? So whenever we try to calculate the CDF of y at some point greater than 2, this case will arise. Okay, since mod of x is a symmetric function, it will distribute the ranges in symmetric way. Okay, so x will be between minus 2.5 to 2.5 in this case. So when we try to calculate the CDF of y at some point greater than 2, it will lead to this case. Okay, and how do we write this probability in terms of integration? We can write it as this: integrate the PDF of x, okay, from minus 2.5 to 2. So integrate it from the lower range. Okay, what is the lower range? It will be minus of that value up to 2. So this will be the case for CDF of points at values greater than 2. But we can directly achieve the CDF of y at points below 2. So let's try to calculate the same CDF in the general case. So here we had written this CDF formula for the CDF. Now we can break it into two parts. So let's consider the case when case 1, when y falls in the range 0 to 2. In that case, what we can do is we can replace it with 1 by 5, the PDF of x. Okay, we can integrate this because we don't need to do any thing here, right? So whenever we have to calculate the CDF of y at points below 2, we can just do the integration like this. Okay, directly putting the PDF of x and integrating it. So we will get x by 5 from minus y to plus y. It will be equal to 2y by 5. So this will be the CDF of y at points between 0 and 2. Now let's consider the second case when y falls in the range 2 and 3. Okay, so this is the second case that we considered here. Okay, that was the specific case, and here we are calculating the general case. So we will write the same thing here also. It will be this quantity. Okay, now we can always break down this into two parts. When the range of y is between minus y to 2, 1 by 5 dx plus 2 to y. So it will be equal to 1 by 5 dx. Now observe here that y, the value of y will always be greater than 2, right? Because y falls in the range 2 and 3. So this probability will go down to 0. This integration will go down to 0, because this is the probability that x will take values greater than 2. Since x has a range only up to 2, right? Here we have noted it here. So x has a range only up to 2. It cannot take values greater than 2. So this value will go down to 0. And we will finally have minus y to 2, 1 by 5 dx. We can write it as x by 5 integrated from minus y to 2. Finally, we will have 2 plus y by 5. So let's first write everything at one place. So CDF of y, it is Fy of y, it is equal to 2y by 5 for points in the range, okay, when y falls in the range 0 to 2, and it is equal to 2 plus y by 5 when y falls in the range 2 to 3. So how do we write the PDF of y? It will be, just differentiate the CDF here, right? So it will be 2 by 5 here for points in the range 0 and 2, and for points in the range 2 and 3 it will be just 1 by 5. Okay, so 1 by 5. So we have finally found the PDF, and this is a general way, okay, in which we proceed to find the PDF of any function of any other random variable. But be careful to pay attention to the ranges of the random variables. In this case, we had a symmetric range for this random variable x. Okay, that's why we had to do these two cases thing, right? So we had to break down into two cases and proceed further. If we had a symmetric range, okay, if x would have fallen in the range minus 3 to 3 or minus 2 to 2 or any range, okay, minus x to x, then we won't need such kind of breaking this into two cases. So paying attention to the ranges is key here. So now let's have a look at the graphing of PDF of x and y. Okay, so here you can see I have drawn the PDF of x and PDF of mod of x. So this blue one is the PDF of x, which was equal to 1 by 5. Okay, remember it was equal to 1 by 5, and which is equal to 0.2. So it falls in the range minus 3 to 2, and its value is equal to 0.2, and it is same for all the range, right? So that's why it is a uniform random variable. But this is not true for y. Y has two values, okay, and it's distributed between the ranges. So for some range its value is equal to 0.4, that is 2 by 5, and for some range it is 1 by 5. Okay, so when y falls in the range 0 and 2, it is equal to 2 by 5. Why is that? Can you notice that thing graphically? So let's try to understand this in a more graphical fashion. Okay, so whenever we have a function, we consider it as some mapping between one variable to another variable. Okay, here in this case it can be considered as x maps to y. Okay, so for any particular value of y, we have some values that x can take. Okay, in this case, when y falls in the range 0 and 2, okay, it corresponds to two values that x can take. Okay, suppose y has value 1. In that case, x takes value minus 1 or plus 1. Okay, so that's why both the probabilities are being added up to 2. So that's why we can observe here that the PDF at those points is double the PDF than what it is there for x. But for rest of the points, for y in the range 2 and 3, okay, there is no component of x. Okay, there is no component of x in the positive side. There is only a component of x in the negative side. Okay, so that's why its value is equal to just 1 by 5 in this range for y.